let us solve few more questions on AC circuits. Here we have a circuit and we have to find the current I flowing through this 1 ohm resistance. Let me put a bar to indicate the phasor value. Okay, and this is a multiple choice question. We have 4 options, and since we can choose from these 4 options, we may solve this circuit a little approximately to save some time. Okay. So first, find out the impedance of this inductor, which will be J omega L. Omega is given 1000 and L is 20 milli. So this will come out to be 20 J ohm. Then the impedance of this capacitor will be minus J by omega C, that is equal to minus J by 1000 into 50 and micro, so 10 to the power 6 above. So that will be equal to minus J into 20 ohm. Okay, this is also in ohm. Now you watch that the impedance of this capacitor is much larger compared to that of this uh, resistance in magnitude. Therefore, the current that flows through the inductor will go almost completely through this resistor, and the current through the capacitor will be negligible. So therefore, this current can also be written as approximately equal to I bar. Okay. Then we can find the value of I bar equal to this voltage 20 angle 0 degree in volt divided by the impedances. So J20 ohm plus 1 ohm. And we can neglect this minus J20 ohm impedance, which is in parallel with a much smaller impedance. So this impedance can be neglected. So this is the value of I bar approximately. Then this is again approximately equal to 20 by J20, which is equal to minus J ampere. Now we see that the first option given is same as our approximately calculated current. So this should be the correct answer because all other options are quite far from this approximate value. Okay, so let us move to the next question. We have to find the equivalent impedance ZEQ for this infinite ladder circuit. Okay, so we have this infinite circuit continuing forever, and we have to find the impedance ZEQ as seen from here. You can call it ZEQ bar to represent a complex number. Now notice that considering this part of the circuit, this part onwards from here to up to the extreme right side, the impedance here also is ZEQ bar as seen from the left side. Okay. So therefore we can write that this ZEQ bar, ZEQ is equal to this J9 ohm, J9, then after that we have J5 and minus J1, so they together is plus J4, in parallel with another ZEQ plus ZEQ. Okay, so from this we can write ZEQ is equal to J9 plus J4 Z equivalent divided by J4 plus Z equivalent. Okay, let us now multiply this denominator throughout this equation. So we will have J4 Z equivalent plus Z equivalent squared equal to J 4J9 plus J9Z equivalent, okay, and plus J4Z equivalent. Now, this term and this term cancel each other, and we can write from here Z equivalent squared, then minus J9Z equivalent, and minus 36J square is plus 36 equal to 0. So we have a quadratic equation and we can solve this equation to get equivalent Z. So we have from here Z equivalent equal to minus of this coefficient, that is J9 plus minus root over 9 squared is 81 and minus 81, and 4 into 36 is 144 minus, then divided by 2. So from this we get J9 plus or minus J root over, this is 225 is 15 by 2. So we have two possible answers. One will be J12, another will be minus J3. Now, minus J3 cannot be the answer because minus J3 represents a capacitive impedance. Okay. However, we see that the impedance here should be inductive in nature, because when you consider these two together, so inductance is much, inductive impedance is higher than the capacitive impedance. So this branch is inductive. With that, in series, we have another inductive impedance, then again something inductive in parallel, and so on. It continues forever. So finally, the result must be inductive in nature. Okay, so the circuit is inductive. The circuit is inductive. From that, we can conclude Z equivalent is J12. Okay, so let's move to the next question. Okay, here a circuit is given. The voltage Vt, which is here, across the terminals A and B, is a sinusoidal voltage with frequency omega 100 radian per second. When the inductor current I is in phase with the voltage V, that means this current and this voltage, they are in phase, then the magnitude of the impedance Z, that is the total impedance, is how much. So how much is this total impedance Z when this voltage V and this current I are in phase? Okay, when this voltage and this current I are in phase, when V and I are in phase, in same phase, then the impedance Z must be a real number. Then Z must be a real number. Otherwise, the voltage and current cannot be in the same phase. So this is the observation. Now let us write the expression for this Z. Okay. So Z, we can write this is equal to this inductive impedance of j omega L plus this two parallel combination. Okay, so we have 100 ohm in parallel with this capacitor, that is minus j by omega c. Omega is given to be 100, so 100, and c is again 100 micro, so 100 divided by 10 to the power 6. This is in ohm. This is equal to j omega L plus 100, and this is minus j 100, parallel minus j 100 ohm. This is equal to j omega L plus 100 into minus j 100 divided by 100 minus j 100. This is in ohm. Let us simplify this. So we have j omega L plus 100, okay, and then minus j by 1 minus j. This is in ohm. We have divided the numerator and the denominator by 100. Next, we can also multiply the numerator and the denominator with 1 plus j. Here also 1 plus j ohm. So this is j omega L plus 100. The denominator will be 2, and when you multiply, you will get 1 minus j. This is in ohm. Now we know that Z is a real number, so the imaginary part of this expression should vanish. So j omega L must be equal to the imaginary part of this term. Okay, so they will cancel each other, and finally we will have 100 by 250 ohm. That is the answer. So now we move on to the next question. Okay, in this question, the circuit is excited by a sinusoidal source, and we have to find out the value of resistance R such that the admittance of the circuit becomes a pure conductance at all frequencies. Now, the admittance of this circuit, that is these two parallel branches, is given by Y equal to 1 over R plus JXL, where JXL is the impedance of this inductor, and plus 1 by R plus JXC, where Jx, this should be minus, where minus Jxc is the impedance of this capacitor. So this is the sum of the two admittances for these two parallel paths. Now this is equal to R minus JXL divided by R square plus XL squared plus R minus JXC divided by R square plus XC squared. This should be plus. Okay, now the imaginary part of this admittance, this complex number, is equal to minus JXL by R squared plus XL squared plus JXC by R squared plus XC squared. And we need this imaginary part to be equal to 0 according to the question, because we have to find out the value of R for which this admittance becomes a pure conductance or a real number. Okay, so from this we get XL R squared plus XL XC squared. This should be equal to XCR squared plus XCXL squared. Okay, so from this we have R squared XL minus XC equal to XL XC multiplied by XL minus XC. Now, this term XL minus XC is not equal to 0. This cannot be 0 at all frequencies. It may be equal to 0 at a particular frequency, but the condition that we are looking for is that is to be valid at all frequencies. Therefore, XL minus XC cannot be 0 at all frequencies, and thus we can cancel this term from both the sides. From this, we have R equal to square root of XL XC. So that is square root of omega L divided by omega C, that is square root of L by C. Now L is given as 0.02 Henry, so 0.02 Henry, and C is 100 microfarad, so 100, and here 10 to the power 6, and square root of this quantity. This will be in ohm because everything is in SI units, equal to root over 200 ohm. And that is the answer. Okay, now we move on to the next question. Here in this circuit, the supply voltage, this voltage is given 10 sine 1000 t, and we have to find the peak value of the steady state current through 1 ohm resistor. That means this resistor. We have to find the current flowing through this resistor. Okay, so first notice that omega is given as 1000 radian per second, and then let us find out the impedances of these inductors and capacitors. Now, starting from this 2 microfarad capacitor, the impedance is 1 by j omega c, which is equal to minus j by omega is 1000 and c is 2 microfarad, so 2 and 10 to the power 6. So this is in ohm, which is equal to minus j 500 ohm. Then for this inductor, 500 millihenry inductor, the impedance is j omega L, which is equal to j into 1000 into L is 500 millihenry. So this will be in ohm, which is equal to plus j 500 ohm. Similarly, the impedance of this 250 micro farad capacitor will be 1 by j omega c equal to 1 by or minus j by 1000 and c is 250 micro, so 250 and 10 to the power 6 here. This is in ohm, so this is equal to minus j 4 ohm. And finally, for this 4 millihenry inductor, the impedance is j omega L equal to j into 1000 into 4 milli. So this is equal to j4 ohm. Okay, now next notice that the parallel combination of these two branches, okay, so which is minus j4 and plus j4, okay, minus j4 and plus j4 is equivalent to minus j4 into plus j4 divided by minus j4 plus j4 is equal to infinity. And in the same way, the parallel combination of this inductor and capacitor, that is minus j500 in parallel with plus j500, is also equal to infinity. So therefore, this parallel combination offers infinite impedance. Similarly, this parallel combination also offers infinite impedance. So no current will flow here or here. Similarly, here also the current is 0, here also the current is 0. So the current will flow from the source in this path, from here, call it I, then it goes through this 4 ohm resistance, I, then it goes through this 1 ohm resistance, and finally through the 5 ohm resistance back to the source. Okay, so how much will be this current I? This current I will be this voltage in sine 1000 t divided by the total resistance in this path, which is 4 plus 1 plus 5, 4 plus 1 plus 5, total 10 ohm. So this is equal to 1 sine 1000 t. Therefore, the peak value of the current, this current I, which is flowing through the 1 ohm resistor, is, call it I peak, equal to 1 ampere. That is the answer. Okay, so now let us move to the next question. A circuit is given where we have a source in series with a pure resistance in series with a inductive coil. The coil has some inductance as well as some resistance. Okay, and the source voltage is 100 volt RMS, and we have to find the possible values of resistance voltage VR and the coil voltage VC. Okay, so we have four possible options given, that VR is equal to 65 and V coil is 35. This is one option. Next option is both VR and V coil are 50 volts. Then VR 60 and VC 90 volts. And finally VR 60 and VC 80. Which among these four possible uh, options, which is correct? We will first draw the phasor diagram for this circuit. Suppose the current here is I bar, that means phasor value of the current, okay? And the voltage of the source, let that be V is bar, phasor voltage, and the voltage across the resistance is, say, VR bar, and similarly the voltage across this coil, let that be VC bar plus minus. Then let us draw the phasor diagram starting from the current I. If this is the current I bar, then the phasor voltage VR across the resistor will be in the same phase as the current. So this will be VR bar, and then the coil voltage will be leading this current. Okay, so that will be somewhere here. That is VC bar. Now, how much will be the angle between this coil voltage and the coil current? That depends on the values of this coil inductance and coil resistance. Okay? If the inductance of the coil is much higher compared to the coil resistance, in that case, the voltage VC will lead the current almost by 90 degree. Okay, but it cannot lead the current with an angle more than 90 degree. And if this resistance is larger compared to the inductance, then the angle between the coil voltage and coil current will have a smaller value. So this angle, if you call that theta, that can vary from 0 to 90 degree. So 0 degree is less than theta, less than 90 degree. Next, for any particular value of VC, coil voltage, if we add VC with VR, then we will get the total voltage or resultant voltage, which is equal to the source voltage Vs. So Vs bar is equal to Vc bar plus Vr bar, and then the magnitude of source voltage we can write as Vs, that is the magnitude of Vs bar, square of that will be equal to Vc square, magnitude of coil voltage plus magnitude of resistor voltage square, plus 2 into Vc Vr cosine angle between Vc and Vr, that is theta, cosine theta. Now theta is strictly greater than 0 and strictly less than 90 degree, because we are assuming the coil resistance is not strictly 0 and coil inductance is of course not equal to 0. So therefore we can write Vs squared is uh, less than Vr plus Vc whole squared. Okay? Because cos theta is less than 1, which means Vs is less than Vr plus Vc. The magnitude of the source voltage should be less than the sum of the magnitudes of resistor voltage and coil voltage. Also, Vs squared is greater than Vc square plus Vr squared because cos theta is not 0. Okay, so now let us see which among these four options satisfy these two conditions. This is one condition, and here is another condition. In the first option, we see the sum of VR and VC is 100, which is equal to the source voltage. So that is violating this first condition. So this cannot be an answer. Similarly, in the second option, again VR plus VC is equal to VS, but VS should be less than VR plus VC, so this cannot be the answer. Next, in the fourth one, we see that 60 square plus 80 square is equal to 100 square. So we have VS square equal to VC square plus VR square, but VS square should be greater than the VC square plus VR square. So the second condition is not satisfied. So this cannot be the answer. Finally, this third option implies that 60 square plus 90 square is actually greater than 100 square. So VA square is becoming less than VR square plus VC square. Again, the second condition is violated. So this also is not correct. So none of the given answers are correct in this question. So all options are wrong in this question. Let us go to the next question. The RMS value of current IT in this circuit is how much? So how much is this current? The source voltage is 1 sine t, which means omega is equal to 1. Then the impedance of this capacitor will be minus J by omega C. Omega is 1, C is also 1. So this is minus J. The inductor impedance is J omega L. Omega is 1 and L is also 1. So we see that the sum of the capacitor impedance and the inductor impedance is 0. So therefore, this path will act like a short circuit path to this particular frequency of the source. So therefore, here we have a short circuit path, and in parallel with that there is a resistance, but no current will go through this resistance because this is shunted by a short circuit. And then this current IT will be equal to this voltage divided by this 1 ohm. Voltage is 1 sine t volt divided by this 1 ohm. So this is equal to 1 sine t ampere. So the RMS value of this current IRMS will be this amplitude divided by root 2, 1 by root 2 ampere. Okay, so that was the answer. Now this is the next question. Here we have an series RLC circuit R, L and C in series, and this is excited by some AC source. Let the frequency be omega and the voltage across this RLC combination is V bar phasor voltage, and the current through them is I bar phasor current. Now the values of this voltage and current are given at two particular frequencies, omega 1 1 kiloradian per second and omega 2 2 kiloradian per second. From that we have to find the values of R, L and C. Notice that at omega 2 the voltage and current, they are in same phase. That means this is the resonant frequency. So at this frequency at omega 2, which is 2 kiloradian per second, let the inductor impedance be Jx, then the capacitor impedance will be minus Jx. Okay, then the current I bar equal to voltage divided by the resistance. Now the value of this voltage and current are given. Voltage is 100 volt and current is 2 ampere. From that we get R equal to 100 by 2, 50 ohm. Next, consider what happens at omega 1, which is 1 kiloradian per second. Now the inductor impedance will be half of the previous impedance. So it will be Jx by 2 because the frequency is halved, but the capacitor impedance will be twice of the previous value, so minus J2x. Okay, then now the value of the voltage is 100 angle 0 degree and the current is 0.03 angle 31 degree. The current is leading because the capacitor impedance is larger in magnitude than that of the inductor. Okay. And we can write that tan 31 degree will be equal to the reactance of the circuit, which is the capacitive reactance, which is 2x minus half x divided by the resistance, which is 50 ohm. From this, we can write 1.5x by 50 ohm is equal to tan 31 degree, which is equal to 0.6. So we have x equal to 0.6 into ohm by 1.5, which is equal to 30 by 1.5 means 20 ohm. Okay, and this X is the impedance of the inductor at 2 kiloradian per second. So this is equal to 2 kiloradian per second multiplied by L. From here we get L is equal to 10 millihenry. And also this X is the impedance of the capacitor at 2 kiloradian per second. So we can write X equal to 20 ohm is equal to 1 by omega C. Omega is 2000 radian per second multiplied by C. So this implies C is equal to 1 by 40 millifarad, or we can write this is 1000 by 40 microfarad, which is equal to 25 microfarad. That is the answer.